So this is the problem, so let's move on to the solution. So in part A, we're told to find the charge density. And to do that, we can actually use Gauss's law. So the Gauss law tells us that the divergence of the electric field is equal to the charge density divided by epsilon. And then we're also given in the problem that the electric field is equal to kr to the power of 3 times the r vector. And so using this, we can actually compute the divergence and then find the charge density. So what is the divergence of the electric field? And up here we have the formula for calculating the divergence in spherical coordinates. So I just copied this out of the textbook. So notice that there's only an r component in an electric field, so we can actually just ignore these components here. So we can just focus on the r component. So using that formula, we see that the divergence is equal to this expression here. So r squared times kr to the power of 3. And this is fairly easy to calculate. We have kr to the power of 5. Differentiating this, 5kr to the power of 4 divided by r squared. So 5kr squared. So this is the divergence. And because of Gauss' law, we know that this is equal to the charge density divided by epsilon. So the charge density is equal to 5 epsilon kr squared. So this is our answer to part A. So moving on to part B, we're told to find the charge within a sphere with a radius of r. And it tells us to solve this problem in two ways. So let's consider the first method. So the first method would be to calculate the total amount of charge directly. So we have the charge density, so we can just integrate through the region of the sphere to find the total amount of charge inside. So we multiply the charge density with dV, so a unit of volume, which in spherical coordinates is r squared sine theta, dr d theta d phi. So dr goes from 0 to r, theta goes from 0 to pi, phi goes from 0 to 2 pi. So let me just pull these constants out. So notice that there are no phi terms inside, so we can just get the 2 pi out. And then we have r to the power of 4, and then we're integrating this from 0 to r, so that ends up with r to the power of 5 divided by 5. And then we're integrating a sine theta from 0 to pi, and that is actually equal to 2, because this is equal to negative cosine of theta, 0 to pi. Cosine of pi is equal to negative 1, so minus negative 1. And then cosine of 0 is equal to 1, so we have minus negative 1. So this is equal to 2. So we also have another 2 here. So the 5's cancel out, so we're left with 4 epsilon k pi r to the power of 5. So this is our answer. But then we're also told to solve this problem in two ways, so let's try a different method. So the second method that we're going to use is to use Gauss' law. So we're told that the flux through a closed surface is equal to the total amount of charge inside that surface divided by epsilon. So what we're trying to find here is Q. So all we have to do is to evaluate this. Well, recall that our electric field is equal to kr to the power of 3 times the r vector. And you see that because this is a sphere, the electric field is always orthogonal to the surface of the sphere. And because of that, because of this special property, so it's always orthogonal to the surface. And because of this special property, the flux becomes really easy to calculate, considering that we're considering the surface that we're considering is this sphere with a radius of r. And so because of this, because the flux is always orthogonal to the surface, we can just, to evaluate this expression here, we can just multiply the electric field evaluated at the surface by the surface area, 4 pi r squared. So Q divided by epsilon. And so rearranging, we get Q is equal to 4k epsilon pi r to the power of 5. And you see that this matches exactly with what we had before. So this is the answer to this problem.